Hi, everyone. Welcome to our webinar, Gas Laws in a Jiffy. I'd like to introduce you to your presenters. First is Melissa Hill. She's going to be helping to answer questions in the background, and she has a background in chemistry. She has 7 years of teaching experience at the college level, including chemistry, biochemistry, organic chemistry, and spectroscopy. And she has 10 years and more years at Vernier. So she is also involved in our product development, faculty training, curriculum development, and project management. And your main presenter, Noose, has 34 years of high school chemistry and physics teacher experience in Frederick County, Maryland. And he joined Vernier as an employee. He's been working with us a long time as a consultant, but he joined us 5 years ago. And he also does a lot of training with educators and curriculum development and technical support. So I'm going to pass it over to Noose to start the webinar.
All right, thanks, Angie. So when we were planning these summer webinars, we're trying to think about, what's going to be the most useful for teachers. And so the last one was like first day of school thing. And this one is one that I really enjoyed teaching this, and I really would like sharing it with you all. And it's kind of the forgotten parts of gas laws, right? People teach all these concepts, but how do you demonstrate them? How do you make them come alive for students? Do you use a PhET simulation or do you use some other thing? You don't have to. You can do real live data collection. And when you're talking about kinetic molecular theory or ideal gas law, how do all the bits and pieces fit together? So that's what we're going to do, and it's super simple. I mean, the setup you're going to see in a minute is not much to it, but I'm going to share all that with you, and then we're going to do some live data collection through the internet. So if you guys want to see how remote data collection works, we'll set you up with that, and you'll have a couple of weeks to fiddle with it. And then any questions or anything like that, please let us know. Vernier, as Angie said, I work for Vernier. I've worked for Vernier for 5 years. I used Vernier equipment since 1984. I met this young physics teacher from Oregon that was writing all this great code and saved me a lot of time. So, I've been using this stuff for a long time. It's all about teachers. All of us are teachers in tech support. And so, we're here for you. And part of the reason why I like doing these too, and especially when we do them face to face, I like freebies. Every teacher likes freebies, and so there's a folder that you'll all get access to. That this folder where I put a bunch of stuff for you. You're welcome to access it at any time. And also, we're going to give you a free copy of Graphical Analysis, 2-week free copy, so not forever, but you will get a free copy of Graphical Analysis. So let's take a look at the setup. Do you have to have brand new sensors? I was just talking to a college professor not even 45 minutes ago, and he wants to upgrade everything. And I told him, I said, why? And he says, well, we have old stuff. I said, well, how old is it? And turns out that, yeah, GoDirect sensors are marvelous. I'm going to be using them today, but you could do this experiment with LabQuest sensors, the ones that you probably already have if you're one of our customers. And so this picture in here is to point that out, that you can do it either way. Hey, do you see my high-tech flask? Lab calls for all these water baths, and I used to use cut-off 2-liter bottles. Works great, and I'm going to use that today. And then notice where I clamped the flask and syringe, because that's going to be something we'll talk about later. So there's a page here. I'm not going to belabor it, except this number down here. We'll deal with that here in just a second. But you can get a copy of Graphical Analysis. People ask me, I'm a Logger Pro guy from whenever, from way back. But if I was in the classroom now, I would switch over to Graphical Analysis in a heartbeat. It's just got everything for a chemistry teacher, everything. And honestly, even for physics folks, it's getting more and more good stuff in there. So highly recommend you look at that if you're, especially if your students are on Chromebooks or something like that. Hey, well, this code at the bottom here is what we're going to use, and we're going to get to that in just a second. So let's do this live demo. So here's what we're going to do. Okay, this is my computer. This is my iPad. Okay. And so if you have graphical analysis on your device, and if it's possible and you have this on a second device like your phone or something, that way you can watch me while you're fiddling around with graphical analysis. But launch graphical analysis and you should get a screen that looks really similar to either one of these. If you have the most current version of graphical analysis, you'll see this box. In your case, it probably doesn't have anything in it. And so this is how you make free graphical analysis into the pro version. So this code that I'm giving you today, it's good for a couple of weeks. So you guys can fiddle around with it after the webinar. We sell codes for their annual codes. And the way our subscription works is it's for your whole school. So there's a code for less than 100 students, and there's a little more expensive subscription for more than 100 students. Is it 100, Melissa, or is it 200? I can't remember now. I gotta have to look that up. I don't remember. They've been fiddling around with that, but it's we don't sell it per seat. We sell it for your school, and so we can accommodate you whichever size school you have. If you have a little larger school, it's a little more expensive. So what you need to do is, I think we're gonna paste this code into the chat if you want to copy and paste it, or it's not too bad. You could type that if you're on an iPhone or something like that. Be careful. It's a capital I and a 1. We need to talk sternly to our software guys, because we don't like that. It's a little hard to see. Capital I 1 dash capital R capital J dash capital Y capital D and small case X. So if you type that in the box and you click submit, okay, then you should get that little red thing at the bottom. Let me do it on my iPad. So this is the way it might look like for you guys. Okay. So then we should be ready to go. Okay, just leave it on this screen. If you happen to get off the screen, you can get back to it by going to the file menu and doing a new experiment. What I'm going to do right now is I am going to set up the first experiment. And if you might remember, I talked about doing this backwards. I'm going to do Avogadro. I'm going to look at gas, the number of molecules, and the pressure, what the effect is on those two. And kind of seems obvious until you go one step further with your students. And I'll show you what I mean in just a second here. So I'm going to connect my sensors on my end here. Okay, and I've got a pressure sensor and a temperature sensor connected. We're going to only need pressure here in a minute, but and then on your end, you can connect to me, but I'm going to hold off for that for just a second. So I'm going with graphical analysis. I just want one graph. I don't need two. So for this experiment, so I'm going to change this to one graph. And then what I'm going to do is for looking at, let me go back to the presentation here. For pressure versus number of molecules, we don't have a sensor that measures in moles, but we do have a sensor that measures in volume. And doesn't measure in volume, but we have a way to record volume, and then we'll relate that to moles. So let's get back to the experiment. And so what I'm going to do is I'm going to use a mode of data collection that is called events with entry. So to change data collection in our software, you need to find the mode option, graphical analysis, bottom left. You guys can just watch. You don't need to do anything right now. I'm going to set it all up, and then I'll share it with you once I have it set up. So I'm going to change to events with entry. What we're going to do is I'm going to collect pressure data with this pressure sensor, and I'm going to then put in volume data, and the volume data I'm going to put in is going to be the volume added. So I'm going to add a gas to a flask here, and you'll see that in just a minute, and of course in milliliters. And so that's going to be our events mode. And you'll notice that at the top here, now I have a keep key, I've got a table. And so now let's get you guys set up so that you can see the data come to you live while I collect it. So what I need to do is I need to set up what's known as a remote data sharing option. See the little TIE fighter at the top of the screen here? I'm going to tap on that little TIE fighter, and I'm going to start a remote data session with you. So I'm going to tap on start session, and it's going to give me a special code. Let me make it big. So that's the code. What I need you to do on your end is tap on data sharing. So I'm going to do that with my iPad right now. Okay, and it's asking me for that code. So once you've tapped on data sharing, you need to type that code in the box there. So I'm going to type it in, RNG, and then the number 3, and then VW. We asked the software guys to make these as simple as possible because we knew that people on phones and iPads and stuff kind of have a, a bit of a limit on, how you can type and copy and paste and stuff. And so I'm going to let Melissa or Angie grab that code and put it in, like, chat or something. We may need to get back to it later. So, and I can too, but as a teacher, but I want to move on here because I only have an hour with you guys and I want to use the time well. So let's take a look at the setup. Here is my setup. I've got a 125 milliliter flask connected to the accessories that come with the pressure sensor. So I've got I've got a syringe and I've got this two-hole stopper. And what I'm going to do to start with is I'm going to just use plain old air in the syringe. So I'm going to fill the syringe with 20 cc's of air. Those you purists that like cc's over milliliters, more power to you. Okay, I know some people are like, with gases, shouldn't it be cc's? I agree. Okay, but sometimes we just have to do what we have to do. All right, so it's all ready. Now, watch your screen on your graphical analysis when I tap on collect. So I'm going to tap on collect. I'm the teacher now, you're the student on your end, and you should see graphical analysis showing you that data is coming in. Look, it's saying collecting. Oh wow, that's really boring news. That's like, looking at it. All right, let's do this. I'm not gonna, this is my first point. I'm not putting any air in. Okay, so I'm gonna tap keep, and it's gonna say, how much did you put in? Nothing, I didn't put any air in. Okay, keep that point. Okay, now let me inject 5 cc's of air, close the valve. That'll save me from having to hold it. I'm going to watch the pressure. Now, there's a little itty bitty meter down here. You can also turn on a larger meter if you want. It's in this box and boxes of view options menu. You could have a little bit larger meter if you want to see that. Turn that thing off. So let me keep that point, and it says, how much volume did I add? I added 5 milliliters. Keep that point. Okay, let's do another 5 milliliters. So I'll open the valve, 5 more milliliters, close the valve, wait till the pressure stops changing, tap keep. How much did I put in? Well, I actually put in 10. Okay, put 5 more, but I've got a total of 10 in there now. Okay, let's do it again. So 5 more milliliters, close the valve. I know you're saying, hey, this isn't very surprising. Hang on to your pants. We definitely have something coming up here that's gonna, I hope, will be of real interest to you, because with my students, it did surprise them a little bit. All right, one more aliquot of air, 5 more milliliters. There's my 20 in there now. Okay, let's keep that. All right, 20 milliliters in there. Now I'm done. So I can tap on stop. One thing to note with events with entry data collection, uses for like titrations with pH meters and stuff like that. If you stop collecting data, it's not the end of the world. If you just say, oh poop, I forgot, I need another data point. Okay, well, you can tap collect and you can append to your data set. So it's not the end of the world. I used to tell my students, don't stop collecting until you're done, and then they would do it by accident. They felt like, oh my, all right, I'm going to change my graph and my view. Guess what? It doesn't do that on your end. You're the student. Yes.
You're still collecting data. Make sure you stop data collection.
I thought I did. I thought I must have hit collect by accident, because now I must have 2 sets. Oh, look at that. Sorry about that. All right, There we go. Sorry about that. Yeah, I must have hit collect by accident or something, or create a new set or something. Anyway, here is the data. You got it too. But now anything that I do on my end, you may need to do it on your end too. Okay, and so you can do the analysis on your end. So what would you do here? What would be the most common thing? What's the relationship between pressure and volume? Okay, pressure and volume added, pardon me, pressure and volume added, okay, is, I probably want to fit a curve. So if you want to do that, then what you want to do is tap on the graph options, the little itty bitty graph guy down here, and then turn on apply curve fit. Okay, it defaults to linear, but there's a whole bunch of them there. With the pro version, you can even put in like custom functions and things like that. So I'll apply that fit. Looks pretty linear. I got 3/9 correlation. Hey, it didn't do that on your end. That's because you're the student. You got the data. You got to do what you got to do. Okay, you're on your own at that point. So if you want to try to do that, then that's great. Okay, now here's the zinger that I've been talking about. Okay, in your shared folder, I put this little chart. I used to put this up on the board in my classroom, and I would have different gases available, and different people will have different ones. Let me get the camera up here so you can see my setup. And so we just did air. Okay, and air, 80% nitrogen and 20% oxygen roughly. So it's got an average molecular weight of about 29. Okay, and we just did that lab, right? We just did the data. So how much did the pressure change? So I can do statistics. So I click on the graph tools option and do view statistics. Let's get that out of the way of the linear curve fit. And we can look and say, oh, it looks like the pressure changed by almost 13 kPa, like 12.97. So let's go look at my table here. And so 12.97, put that up on the board, have your students look at it, and then try a different gas. I used to do Freon back in the day. I totally recommend you don't do that. Okay, but difluoroethane, not bad. It's a duster gas. Let me show you that. This stuff, whoops, get the camera up. There we go. This stuff right here, difluoroethane. You can get that at Office Depot or something like that. Lots of different gases you might have access to, butane. You might have natural gas at your school, so you could use methane. This is kind of cute. You can get the carbon dioxide in these little things to fill up your bike tires with. You can also generate the carbon dioxide, by just dropping an Alka-Seltzer tablet in water. And I used this setup the other day and it worked just fine. But let's do this. Let's say I'm going to do difluoroethane, molecular weight more than twice the molecular weight of air. Okay, let's go back to our graphs. What I'd like you to do, I'm going to close my fits here right now, just so that I have less confusion on the screen. I would like your students, have your students predict, if I used this gas that has double the mass, how's that going to affect the results, right? And so on graphical analysis, bottom left corner, tap on the graph tools, okay, and do add prediction. All right, so just down there at the bottom, add prediction. I would be willing to bet, if we just did a little straw poll here, I would be willing to bet most students are either going to have a higher line like that, or they might have something that has a higher, and then you'll get that one or two students that'll say, oh, it's a trick, it's going to go down, it's not going to go up, or something like that. So have your students predict that. Picking another gas, boy, if you have a touch screen, it's so much nicer to do. I don't have a touch screen on my Mac, but on my iPad I do. So I could go, oh, let's do that, right? So, and then once you got it the way you want it, just tap on save. Okay, so let's do another run with difluoroethane and see, what that looks like. Okay, so let me get the camera up so you guys can see what I'm doing. Here's the duster gas. Let me get my syringe. Want to be careful, it's a little pressurized, so I'm going to take a syringe off, open the valve, and release the pressure. Okay, and then take this valve off. Just got to make sure that the bane of pressure labs is leakage. So you want to make sure everything is nice and the most common repair on pressure sensors is students will break the plastic lure lock connectors. So you want to be careful about that. But anyway, here we go. So I've got the difluoroethane. Let me make sure it's working. Okay, take that and put it in the valve end there, and let's get some gas. Try not to shoot I did open the valve, right? And it is working. Tested this yesterday and it worked great. I just want to make sure I don't have anything obstructing it, because it usually just goes right up in there. Let's see. Oh, there we go. All right. All right. So heavier than air gas. So if I close the valve and flip it upside down, okay, then I can adjust that to 20. So I'm going to open the valve and I'll just shoot out a little bit of gas there. All right, close the valve, stick it on here. Let's see what happens. Okay. Neat thing about graphical analysis is that if you start a new run, you saw me do that by accident a second ago. If you start a new run, it automatically saves the old one. All right, so if I just hit collect, you'll notice that it says collecting on your end, and so I can start doing the same thing, right? I can hit keep, okay, and I haven't put any in yet. You may say, hey, Noose, I can't really tell what's going on. Make sure, a couple of things you might want to check on your end. One is check out, if you tap on the y-axis, we want to make sure that we're seeing the second set of data, right? So you might want to turn that on. Do you want to compare it to the first set? It's up to you. You can turn it on or turn it off. It's your call. We can rename these too. I'll show you that in a little bit later. The other thing you may notice is the table isn't there anymore. If you tap on the view options, you can turn the table on, but you'll notice that stuff that I'm doing doesn't necessarily echo to you. So you may have to adjust it for yourself. So let me get back to the experiment. All right, let's do 5 milliliters. And where's my pressure? There it is, 104. Okay, looks pretty good. Keep that. Do 10 milliliters. Watch that pressure, 107.2, looks pretty steady. 15 milliliters. One 110.5 looks pretty good. Keep that. Let's put that last data point in. 114.1 looks pretty good. Keep that, and I'm done. Okay, so I'll stop collecting data. Now let's compare those graphs. So I'm going to get rid of the table just because the way I have this set up right now, it's a little ugly with the table in there. Let's see. Do I want to see the prediction anymore? Maybe, maybe not. Let's make sure plot 2 is on. I'm going to turn off plot 1. I'll leave the prediction on there. Let's take a look and see. Ooh, interesting. Let's turn plot 2 back, plot 1 back on. Ooh, I can't even see the points. Wait a minute, are they really there? Let's do a couple of things that are kind of good, neat in graphical analysis. You can tap on the little graph tools, dude, and then turn on a legend. Hey, Noose, wouldn't it be nice if we could rename these so we know what we're looking at? Good question. Who asked that question? I'm going to go to the table. So I'm going to turn the table on. And right next to the run, there's 3 little dots. If you tap those 3 little dots right next to the data run data set, you can rename it. So that first one was air. And the second one was difluoroethane. Now notice that the table now is showing, or the legend is showing the right thing. So let's see. So look at that. I mean, they're so on top of each other. Now, the other thing you might fiddle with is the colors. Notice that both pressures are kind of a blue color. Make one of them a different color. Like if you tap on the little color dot there, you can, let's make that one pink or something like that. And then, that way, maybe they can stand out a little bit better, but they are right on top of each other. So, and I'll leave it to you. You've got the data. You can put on 2 graphs if you want and have one run in one graph and the other run in another. So I could have number 1 at the top, just air at the top. I don't think I need the prediction anymore. And I can have my difluoroethane on the bottom, and then do all kinds of fun stuff you can do here, folks. You can do your curve fit separately, right? You could do a curve fit for the top one. You could do a curve fit for the bottom one. You could do the statistics and compare the delta T's, look at those, so, I'm going to do this. I guess the statistics is the most important. That our whole point was, hey, if we double the molecular weight, what does that do? Well, let's see. For the air, the change in pressure was 12 point, almost 13. And for the difluoroethane, the change in pressure was, did I mess something up here? It's interesting. It says 0.6, but I think we noticed that the 2 graphs are right on top of each other. So something's a little.
You have temperature on the y-axis and not pressure.
Thanks, Melissa. I'm glad you were there. It's so easy to get like tunnel vision, right? And look at that and go, wait a minute, but you're totally right. Let's see. 12.9, 12 point, oh, look at that. That's kind of crazy, right? Equal volume, say equal number of molecules at the same temperature and pressure. It's easy to say that. It's easy to talk, but look, we proved, let's try some more gases. Maybe in your classroom, you have different groups do different gases, your call. So I'm going to move on to a new experiment in a second. So my suggestion to you is if you like your data or my data, and actually I kind of like my data too, what you might want to do is on your device, tap where it says Untitled and save that data set. Because I'm going to start a new experiment and you're going to lose your data. So I don't want you to do that if you don't want to. So, save your data, put it somewhere nice and handy. This was P versus N. Okay, so that you can get to it later if you want, because we are going to start a new experiment, and I just want to make sure that if you want that for later, that you don't lose it. Okay, and so remind me, Melissa, at this point to do a new experiment, they do nothing, right?
Correct.
Right. Okay. So what you want to do on your end is just watch for a second. Don't start a new experiment. Save it, but don't start a new experiment. And what I'm going to do, I am going to start a new experiment. Okay. So I'm going to go up here and I'm going to do a new experiment. And I'm sorry I've given you guys a little bit of a bum's rush here, but with I only have half an hour left, I want to get to another one that is certainly intriguing. What I'd like you to do on your end is I'd like you to join my new experiment. Okay, so you need to join my new experiment on your end. Okay, that's why I said you need to save it if you didn't already. Okay, and so this time, what are we going to do? All right, let's think this through. I'm going to do Charles' law, and I'm going to do it a little different. So what's Charles' law? Well, pressure and volume, but pardon me, I said that wrong, didn't I? Volume and temperature. But what we want is we need to keep the pressure constant. And that's the tricky part that Don Volz came up with.
News.
Yes, go ahead.
The graph is covering the video of what you're showing. There we go. Perfect.
Thank you. I need a bigger monitor. Is that what you're telling me? Yeah. Nah. All right. So here's what I'm going to do. This is a little different from the way you might have thought of doing this in the past. First, you'll notice that I'm going to be using cut off 2-liter bottles. Second, I'm going to do something a little unconventional. I'm going to clamp this test tube clamp to this right to the body of the syringe. Now, in this experiment, the syringe is going to, the purpose it's going to serve is 2 points. I need to keep the pressure constant, and I need to know what the volume of the system is. Okay, and so we'll talk about that in a bit, but there's basically the setup. Now I'm going to need I'm going to be able to need to also monitor temperature. Okay, and so let me show you how this works, and then we'll set up graphical analysis together so you can see what I'm doing. Okay, so I'm going to take a water bath here, and this is a salt ice water bath that I set up earlier, so it should be pretty cold. Let me slide it under here. and get everything orientated. Is that a word? Now check that out. If you do this with a flask, well, not so much that, a flat beaker. If you clamp that clamp down at the bottom of the flask, you don't get the whole thing into the water bath. And so that's kind of, small amount of error that, you might be able to improve on by clamping the system right on the syringe, okay? So now let's go to graphical analysis. Notice that it defaults to time. We don't want time. We want to measure the pressure, we want to measure the volume and the temperature. Those are the two things we're most interested in. And so we need to adjust this thing so that we can measure the temperature at different volumes and then plot a graph of that. So I only need one graph. Okay, and I don't need time. I need what's known as selected events data collection. So I'm going to change the mode down here, and I'm going to go to events based. But notice there's two choices. The first one was the one where you type something in. The second one is when you don't type anything in. Okay, well, let's think about this one. The temperature probe is going to measure the temperature. The pressure sensor is going to measure the pressure. But wait a minute, Charles' law, we want the pressure to stay the same. So the pressure is not going to really change. What else is going to change? The volume. So this event down here is going to be volume. And I'll use milliliters again. Okay, and so there's my setup, very similar to what we had before, but not pressure. I want temperature. So for volume will end up being the independent variable, temperature will be the dependent variable. Now let's talk about volume. Okay, what volume of what? Well, it's going to be the volume of the flask, but also all this tubing and stuff. That's all connected. And so what we're going to need to do is we're going to need to monitor all this stuff. Let me open the valve here a little bit so that's all connected. Okay, so now the valve is open, the flask is connected to the pressure sensor. Let's take a look at those values. I'm going to make my graphical analysis screen a little bigger, and I may end up covering over what you guys see, what your student view, but you guys have the student view on your end, so you don't need to see that. So what I need to do first is I need to take note of this pressure. So let's take note of that, because that I need to keep constant. So 94.7 kPa. This is going to be the constant pressure. Okay, so I'm going to take note of that, and I'm going to start collecting data. So here goes. On your end, if everything is working the way I hope it's working, you should see it say collecting data. Okay, and you can see that it is, at least on my iPad it is. Okay, so let's get back over here. Now, it's going to ask me, when I click on keep, it's going to ask me for volume. Volume of what? Volume of all that gas. So in your folder, I put a pre-lab. Okay, take a look at this. You're welcome to use this if you like. Challenge your students to find a way to determine the volume of the gas in the system. Okay, and so this is actually a pre-lab for another experiment. So this is a Google file. You guys can get rid of this line here that says 3 molars HCl because it doesn't apply here. But here's the system. Here's the equipment that you might give your students to find the volume. Now, spoiler alert: fill everything up with water. Weigh it before, weigh it after. The difference will be the volume. But you might let the students, fiddle around. I mean, there's even a volumetric flask there because, the word volume, wouldn't you use a volumetric flask? so yeah, just kind of, but it's kind of fun to see what the kids come up with what's the volume of the system. So 145 milliliters is what I measured in the laboratory. And so I haven't changed the flat, I haven't changed the syringe. It's at the bottom. With this experiment, it's important that the syringe start at the bottom. And so if I keep this value right now, it's going to say, what's the volume? And I'm going to say 145 milliliters. Now, here's the tricky part. Pay attention. This is pretty cool. Going to take the water bath. I'm going to switch water baths. Okay, so raise this up just a hair bit. And I love using 2-liter bottles just because, you know, they're, well, in Oregon, they cost us 10 cents a piece. In Maryland, they didn't cost us anything. Okay. So when I taught in Maryland, you know, didn't have to pay for my plastic bottles. But now that I live in Oregon, which is fine, it encourages people to recycle. So let's see what's going. Oh, that temperature is starting to come up. And so what I need to do is remember this number? I need to get the pressure back to that value. Now, I've got 25 minutes left, so I'm going to give you guys the bum's rush. I apologize. But, you know, ultimately what you want to do is you want to wait about 3 to 5 minutes bare minimum. Okay, I'm going to push the limit. We'll see what my value for absolute zero comes out to be. So what was it? 94.7. So let me get that pressure. Yeah, pretty close, right? Close the valve. Okay. And so then I keep the value and it says, what's the volume? Well, it was 145, but now I've also got 5, 6, 7, 8 milliliters more. So 145 plus 8, 153. Okay. Now I'm only going to do one more point because I just don't have a lot of time. The more points you do, the better, but I will give you a hint. If you're going to use the 20 milliliter syringe that we supply from Vernier, 30 degree water is hottest you can go. Okay, because you'll run out of syringe. Okay, it'll just run out of space. And so to keep your warm water bath around 30 degrees or less. So think about spreading out your water baths. You know, if you put salt in the water, my salt water bath there wasn't as cold as I was hoping it would be. I've had, you know, you can get that thing down to the negatives easy. But today, I don't know, I guess because I talked all that time about the number of moles, like my water bath just got warm. So, but anyway, the whole point here is that we want to keep the pressure constant. I don't know if there's any oldies in the audience, but we used to do this with mercury and capillary tubes when I first started teaching. Crazy, right? But, you know, who knew about mercury back in, well, they probably did know. But anyway, so I'm going to open the valve and adjust the pressure. Like I said, give it 3 to 5 minutes. You know, there's a lot of thermal mass there, and you know, you want to give that thing a chance to equilibrate. But you get the point here. Okay, so let me close that valve. All right, so yeah, not too horrible. So let's grab that value. So 145 plus, let's read the syringe. Syringe reading is 10, 11, 12, 13, 14. Yep. So 145 plus 14, 155, 159. All right. So you do all your water baths and you know, you'll probably get better data, but we're going to call it good here. And so then I'm going to tap on stop. Okay. And so on your end, the data collection should stop too. Now let's have some fun. Okay, I don't need all these numbers here, so I'm just gonna get to the graph. So I'll turn off my data table and the meters. I don't need those right now. So first thing you wanna do, what's the relationship of temperature and volume? So you're gonna do a curve fit. Okay, and we're gonna say, oh, look, it's really linear. Look at that, 3 9s, I got 3 9s correlation. Well, I should say, what do you get? But obviously you're gonna get the same thing as me because you have the same data I do. Now you're gonna have to do it on your own. Me doing this is not going to echo on your screen. So you're going to have to do it on your own. But hey, Noose.
Hey, Noose.
Go.
Oh.
Go ahead. I love that. Go,
this
Melissa.
Is probably the same question you were going to ask, but what did you just do right there that made all your fonts and everything bigger? That sounds like a really good teaching tool.
Oh man, Melissa taught me this one actually. Up the top right the 3 little dots at the top under presentation. Okay, when you're teaching, you can change the magnification of the screen. this might be also good for students, accessibility type things if students have vision issues. But when you're teaching, you can zoom that in very nicely. That's what I just did surreptitiously until Melissa caught me. I want you to notice another thing. B, what is that? Well, that's the point where the volume is 0. Negative 283. Hey guys, what should it be? Negative 273.15. I think I have good error here. This is my value for absolute 0. Isn't that crazy? I think I deserve the Avogadro Award for Chemical Engineer of the Day. Okay, I would give this to my students. They would fight over it. They had to prove to me how they got that. It was crazy. But though it's got to be a real award because look, it's signed by Amedeo Avogadro. Okay, but look, I'm super amazed because my water bath sitting around here. But then again, my delta T value is not too bad. Okay, but yeah. Look at 3/9 correlation, so I got pretty nice plot here. Now check this out. Okay, and I'm sorry, I'm bums rushing you guys. I really feel bad about this, but this very same setup you can also use for another experiment without changing hardly anything. Okay, that's the beauty. As I said, gas laws in a jiffy. You're getting it, folks. You're getting it in a jiffy. I'm saving this one. Wait a minute. If you like it, save it too. I'm saving that one. What was this? This was V versus T. Okay, have pretty good data. I might need that later. I might need to prove to my boss and say, look, I got within, let's think that through. 27 degrees would be 10%. So this is 10, so that's less than half. So I'm under 5%. I'm like 3% error. That's not horrible. Okay, so if you want to save it now because we're going to do another experiment, and that'll be it because I'm with my time left. I won't be able to do well. I want to hope that a lot of people have done Boyle's law, so I'm going to do Gay-Lussac's law. So if you want to save it now because I am going to start a new experiment. What's Gay-Lussac's law? So that's going to be pressure and temperature, right? So we're going to keep the volume constant. Probably the easiest one of these type, and you'll see that in just a second here. So same equipment setup. That the other beauty of this is the equipment setup is identical. It's the same equipment setup. So you have very little that you have to do in between. Now you have 48-minute periods. You might only squeeze one of these in. Okay, but just. So anyway, Gay-Lussac's law, the beauty of it is the volume stays constant. So what I need to do is I'm going to take this apart a little bit, not by much. We used to do these at NSTAs. We do both Gay-Lussac and Charles. We might slip in moles next time. It doesn't really matter what temperature you start at, but I tend to like to start at the cold temperature, so that's where I'm going to go. And what I'm going to do here is I'm going to take the syringe off. I'm giving you time to save the data in case anybody wants to do that. I'm going to take the syringe off and I'm going to zero the system out. So if I can, my hands got wet. All right. Turn this around. You guys going to NSTA next year? I can't wait to see you guys for real. It's one thing to do it this way, but it's so much nicer when you're in the room and you can talk to each other. Okay, so volume of the system is constant. Okay, lower it into the water bath. Hope everybody has saved their data if they wanted to. So I'm going to start a new experiment. Okay, so here we go. New experiment starting now. I'm not going to save it. I did save it, so I'm good. Okay. Yes. Okay. And sensor data collection. This one, the neat thing is it's the same set of sensors, but let's think it through. Gay-Lussac, pressure and temperature. I'm not going to do anything with volume this time. So I need one graph. And I need to change the mode. I don't need time. I need to know temperature and pressure. So I'm going to change the mode to events based. And this time it's going to be selected events. What do you mean selected events? Well, I don't have to do anything. I have a temperature probe. I have a pressure sensor. It's going to do all the work. literally going to do all the work. So selected events, when I hit the button, it grabs a data point. So I'm good. So ready to roll. And I'll start collecting data. Let me get some meters up here. I don't know if you guys notice, I really like that box up there where you can turn different things on. Depending on your screen size, it looks kind of ugly sometimes. So might have to adjust your screen size a little bit there. Let's get this a little prettier here. I'll get the graph over so that's a little prettier. All right, start collecting data. Cold water bath. Yeah, sorry, my cold water bath was definitely colder. It's definitely warmed up a little bit, but for the purposes of the 15 minutes we have left, we'll live with it. And so let me grab the point. Now check this out. I'm going to hit keep, and it's just going to grab a data point. Look at that. It just grabbed a data point. Because I'm the monkey pushing the keep button. So all I got to do now is swap out the water bath. Now in your classroom, think about managing that, right? You could have kids sharing water baths. I mean, I had 12 lab stations. So when I saw the original lab and they were talking about, 5 water baths, 1 liter beakers, it's like I couldn't do that. I just don't have that many. Now you can share them, so I had 6 peninsulas in my classroom. And so I would set up water baths on each peninsula. So kids weren't, even the plastic ones, they weren't just walking around with them because, it'd be kind of dangerous. Not so dangerous with plastic, but you're going to with water everywhere. And so, so I'd set up water baths for them to share, but, plastic bottles, in Oregon, they're 10 cents a piece. In the rest of the country, I don't know about the rest of the country, but Maryland, they were, we would recycle them. Watch the temperature and the pressure. You want those to be, leveled out, not changing. You don't have to have these meters on. The little ones at the bottom are the same. I just kind of like these big ones because I'm old and I can read them even without glasses. Pretty close. Let's keep that value for now so we can talk a little bit at the end. So keep that. Let's get the warm water bath. Now this one, you could definitely use higher water temperatures, but I don't recommend going over 50. Couple of reasons. It's hot, so if kids could get burned. The other thing is that if you pop the sensor, it's not going to hurt anybody, but it's going to be surprising. And that data point, of course, won't be any good, which doesn't matter. I mean, you can always get rid of that data point. We're working on adding strike through to graphical analysis. We don't quite have that yet.
Hey,
but
Noose,
yes.
you're blocking your camera again.
Oh, sorry. Yeah. So what I did was I changed the water bath. So it's the warmer water bath. So you can see it's up to 25. The one before was 16. But yeah, this one you could definitely have much higher water baths. Just be careful. People say, can I go 100? Yeah, you could do 100 degrees, but you'll probably pop the stopper. And that's a high temperature to have kids handling, like this, especially a couple of liters of water. They could get hurt. So anyway, let's see. I'm going to grab that value. All right, and I'm going to stop collecting data. So now you're on your own. Let's see what the relationship looks like. We'll do a curve fit. So go down to the little graph tools dude and pick apply curve fit. Let's see how linear this came out to be. 2 nines correlation. Yeah, I probably should have waited a little longer. We're running out of time and I'm kind of pushing the limit here. So, hey, Noose, what's this event thing down here? Something boogered up on my graph. Sorry, let me see it again. Curve fit. Here we go. Oh, 3 nines. Once I fix that, by the way, what'd you do, Noose? Down here it said event instead of temperature. So I tapped on the y-axis label and I just changed it to temperature. When I did that, I got 3 nines, almost 4. That's pretty decent. Hey, what's my absolute zero value? Swap the axes. So start at the x-axis, swap them. So make the x-axis pressure, make the y-axis temperature. Okay, do another curve fit and the y-intercept should be absolute 0. All right, drum roll. Whoa, look at that. All right, I'm taking that, negative 276.6. Tremendously lucky, but I'll take it.
Nice. Good one.
But look at that, that's like less than 1% error. I mean,
Yeah.
I'd say I'm saving that file. P versus T. Isn't that great that you can measure something like that? But also the idea that you can make ideal gas law come alive, right? We talk about it, we throw it up there, maybe for our more advanced students that need all this little stuff. But honestly, just seeing it, right? Seeing the gas trapped in the container, seeing the data being collected, and then going through the analysis and thinking about the math that's involved with the analysis, I think there's a lot of value in that. So I've been talking continuously for 50 minutes almost. Let me go look at my presentation because I totally forgot about that. Let's see here. A couple of things I wanted to point out, and I'm not really good at this. Melissa's way better than me, but a couple of things to be aware of that are in Pro that you have now. So you're welcome to fiddle around with it. Probably for chemistry teachers, one of the most important features is the fact that, besides remote data, is the fact that you also have built-in data files. And that was something us Logger Pro users for years really missed, is we missed the data files. So if you want to fiddle with that, go to the file menu and start a new experiment. And this time, by the way, if you wanted to save the data, did anyone want to save the data? I'm going fast. So if you want to save the data, do it real quick here. Because I'm going to pick this button right here that says See Experiments. I guess your data won't go anywhere even if I do that. Okay. So built into graphical analysis are a whole bunch. It's kind of like Logger Pro, but it's better because not only is these experiments in here, and you can filter this by I'm going to filter by chemistry because that's what we're doing. But you can also see a video. So for example, let's see, what did we do today that's in here? Did we do any of the ones? Maybe not. Okay. So we'll pull up an experiment. Let's do, I don't know, titrations are, in my view, they're the time-based ones are the best. The events-based ones aren't as great, but there's a video Melissa shot a bunch of videos, and then she's super great at editing and stuff, so kids can see the whole setup. Maybe you have a student that's absent, or maybe a student not quite understanding what's happening, so the students can see the data. They can see we did these to match our manual. So if you own our lab manuals, these included data experiment files are from our lab manuals. We did use GoDirect sensors just because this is all new stuff. But another thing that's super cool is that this data that Melissa collected, it can also be synchronized with the data collection. And this is the part, Melissa, I always screw up. What do I do now? Just click play up here.
So it's already synchronized because you opened a sample file.
Good.
Yeah.
Good. Thank you.
Thank
you.
Yeah, what it's saying, so if you wanted to do this yourself, for instance, if you click on in the little upper left-hand corner, the little movie thingy, so if you're syncing a data yourself, you want to, that's where the data set at 0 time. So that means at the beginning of the data set, you want to sync it to 25 seconds in the video is what this one is synced to. So if you have your own video that you're adding and I did some pre-lab in here. I know it's like 10 seconds into the video that I started data collection. Then you would set data set time at 0 and video at 10. So yeah, that's how you do that.
Yeah.
And then we also have this one going at 3x speed because it's a pretty long video and the data coming in is pretty slow. So you can do it at different speeds. If you're doing a shorter experiment, like a physics quick experiment, you probably want it at 1x or something like that.
So that's one feature that's really cool in graphical analysis. The other thing that's really cool is that you can do this yourself. If you collect a set of data and videotape it while you're doing it, or your students could do it, right? So they could go and collect some data. So I'll throw some quick data up here. So get a quick data file here, something that's time-based. So I gotta plan this better, Melissa. So yeah, I don't want to. I don't. Titrations are fine, but they're not. They're not. Oh, I have some kinetics here. Don't I have some kinetics? I'm pretty sure I do. Here, kinetics, crystal violet. Yeah, I think that'll do. Yeah. So what you could do is you can also insert your own video. So you could have students take a video of while they're collecting data, and then they can also add that video. I apologize. I'm doing this on the fly and I don't have anything prepared, but I could take one of my videos here and I could import them into Graphical Analysis. And like Melissa said, if you could also synchronize it by using these tools up here. And so that's kind of neat. You could have students turn this in as a part of their lab report or whatever. And this is part of Graphical Analysis Pro. If you don't have Pro, you don't lose anything as far as data goes. You just can't do the video stuff. We have customers that say, what if I use Pro and then I don't use Pro later? Your data's fine. But your videos obviously won't show. So those are things to be familiar with. And as far as a chemistry teacher goes, I think that's kind of neat to be able to have the students show you that they set the experiment up and that sort of thing. Bar graphs is new. It was just added last week. I used to do a Pentium isotope lab where I had the students collect the masses of pre-82 and post-82 pennies. This little graph that I put up here, this is using a colorimeter to determine lambda max rather than doing if you don't have a spectrum is. So you could use a bar graph to represent that. I think it looks really, really nice. We actually, you have this slide deck, so I'm not going to read this, but this is what we have done so far with Graphical Analysis Pro compared to free, because we do get a lot of customers say, if I get Pro, what do I get for my money? Well, Melissa made a very nice 2-column thing here, and you can see the comparisons, and then you can also see a couple of the features like data marking that's coming. Strike through is going to be in the free version too. Strike through is when a student collects data but they make a mistake. How do you change that? Okay, so a couple of things before the end here. Melissa and I and Elaine are at chemistry@vernier.com. So if you have a chemistry specific question, write to chemistry@vernier.com. You can always just write to support@vernier.com. We have a chat feature, and if any of us are available for chemistry, they usually tag us. Otherwise, someone's always watching the chat. And so please take advantage of those. This is our support page. You can send us an email. When you call Vernier, you are going to get a human in business hours. Now, be aware, you guys on the East Coast, that we are 3 hours behind you. So if you call during first period planning at 8 a.m., no one's going to answer the phone. So just
Hey Noose, we just had a great question come in. How would you compare GA Pro to Logger Pro?
So I have to be careful. I taught physics for a number of years. Logger Pro has some wonderful built-in video analysis options that we are now offering in a different platform in video analysis. As far as chemistry goes and everything that I taught, GA does it all. Okay, I would not be at all worried about switching to graphical analysis, even the free version for chemistry teachers. The free version has an awful lot in it, and everything that's in our lab manuals you can do with free. You don't need Pro. You don't need Pro for Go Direct sensors. You can collect data with the free version and Go Direct sensors. So how does it compare to Logger Pro? Logger Pro is really complicated. And it's got a lot of stuff that I never used when I was teaching. Pro, the couple of things that I really like, one is the option now to do bar graphs. That's kind of something that I did use occasionally, and I didn't have that. But the fact that it runs on anything. Logger Pro only runs on computers. What's one of our most common Logger Pro questions? Hey, News, how can I get a Logger Pro on a Chromebook? You can't. There is no way to run that. And so graphical analysis is that only option. I will tell you, the chemistry department at Purdue is running graphical analysis on iPads. that's what they're using in their chemistry department at that college. So yeah, it's a very nice piece of software, and it will do, for most of us, it'll do everything you want it to do. Okay.
I would also add to that, because Logger Pro is, you mentioned, it's such an old piece of software, right? So it's really designed for people who learned software in the like 90s and early 2000s, which is not students today. They're used to an app environment. They're used to tapping on things and finding things for themselves. And I find GA and GA Pro to be much more user-friendly, especially for younger people who have come up in the app-based software. You give Logger Pro to a 14-year-old right now, and they've never seen software like that. They're not comfortable with it.
Yeah.
So I find teachers really like the GA and GA Pro much better because they give it to their students, and their students just figure it out, faster than they do. So
I volunteer at a third grade class in Portland, and they use GA on Chromebooks, and the kids have no trouble at all. They're just tapping away because they're touch screen Chromebooks, and they're just, so yeah, I wanted to point out custom expressions has been just recently added to Pro. So those of you that have to be able to put in your own function, you're going to Wolfram Alpha and you're getting some wacky function, you can try it. Okay, we are past time. I really appreciate those of you that have hung out this long. We are not going to log off right away, but I definitely want to respect people's time. So I appreciate your coming. The next one is going to be on spectroscopy. Melissa and I have already started planning it out. Sports drink from AP Chemistry, but it's also got Beer's Law in there. So those of you that don't teach AP, that still has some applications there. And we're going to use LabQuest 3 as our starting spot for that one. So I encourage you, if you have time, I don't know if we have, Angie, do we have a date yet for the third one? I don't know if Angie's still there.
Do just one moment.
I'm going to stop sharing because I don't think my screen's that important anymore. I think I have it on my calendar, but I don't remember. It's a couple, 3 weeks down the road, I think.
It's on August 12th.
Okay, there you go. So August 12th, the central point will be the sports drink experiment from College Board, experiment number 1, that's been modified to use Vernier sensors. And I've got a bunch of extra stuff there that I'm going to share with folks to help you to do that experiment and be successful. So I hope some of you can make it. I look forward to seeing you all. Otherwise, have a great, let's see, we are on the West Coast. So for most of you, probably a great afternoon, unless you're with us on the West Coast, which I'm sorry, it's afternoon. It's all afternoon for everybody. Have a good day, folks.